Well, this is Electric Circuits course of second semester students in the Department of Electrical Engineering. This is the textbook, and we are discussing chapter 4. In previous lectures, we have discussed 4.1, 4.2, and a part of 4.3. And in today's lecture, I will say few words on this, and then operational amplifier circuit design. Now, the symbol of operational amplifier, as you know, this is the symbol of operational amplifier with two inputs. Input with positive sign over here is known as non-inverting input, and input with negative sign, I mean the negative sign, this negative sign, this is inverting input. We can also show we can also see VP and VN over here. So sometimes this VP voltage here is the voltage with respect to this common ground, and voltage here is Vn with respect to the common ground. Plus VCC dual voltage supply is used usually in operational amplifiers, but operational amplifiers can be used with single supply, and in case of single supply, this is our ground. Minus VCC is connected to ground. Usually these plus VCC and minus VCC in the symbol, it is not used. It is understood that it has plus VCC and minus VCC, dual voltage supply. And we can show this VP and VN over here. Simply, this is VP and VN. This P means with positive sign and N with the negative sign. P is non-inverting input, and Vn is inverting input. The current entering through this input is labeled as IP, and entering through this is labeled as IN. Note that these are only the reference directions of the current, of these two currents. As we have discussed in the previous lecture, that the output voltage is the gain A, voltage gain A multiplied by the voltage difference over here between these two inputs, VP and VN. So the voltage difference VP minus VN is known as differential voltage VD. Another thing with operational amplifiers is that maximum output voltage will be plus VCC and minimum output voltage will be minus VCC. In practical circuits, this maximum output voltage will be little less than VCC, and minimum output voltage will be little more than or above minus VCC level. Operational amplifiers, they can operate in three modes. Mode number one, known as plus saturation mode. When AVD, when the product of A and VD again, this VD means VD is the voltage difference between VP and VN, as shown in this VP and VN. This is very important, VP and VN, the voltage difference between these two inputs. When the product of A and VD is greater than VCC, the output voltage will be at plus VCC and it cannot exceed this level. Minus saturation mode means when when the product of voltage amplification and the differential input voltage is less than minus VCC, then the output voltage will stuck at minus VCC level. In linear mode, when the product of A and VD, I am taking the mod value of disregarding the sign, when the product is less than VCC, if the product over here is less than VCC, this is known as linear mode. Now, we assume that A is a typical value, A is 10 raised to the power 6, and what is VO? VO is AVD, so 10 raised to the power 6 VD. We also know that VO maximum can be 15 volt. Instead of this 15 volt, I will say it can be VCC. VCC, maximum VCC and minimum minus VCC. So, if we consider maximum voltage, it cannot exceed plus VCC level, and this is AVD then. Now, if we assume VCC along with this VCC as plus 15 volt, VCC is plus 15 volt, and minus VCC as minus 15 volt, then this will be 15 plus 15 and AVD. Now we can say what is the differential voltage for which we will have maximum output voltage. So from here, so as we have assumed A as 10 raised to the power 6, so it is 15 microvolt. This is very important thing. So when VD is equal to 15 microvolt, the output voltage is equal to plus 15 volt. Means, look at this VI graph. So if VD, this VD, which is VP minus VN shown over here, when it is 15 microvolt, the output voltage on this axis is 15 microvolt. Is 15 volts as shown over here. And when this VDD is minus 15 microvolt, the output voltage is over here. This is the output voltage. So when the differential voltage is between these two values, between minus 15 volt to plus 15 volt, the output will vary from minus 15 volt to plus 15 volt. But when this VD or differential voltage is greater than plus 15 microvolt, so the output voltage will stuck at plus VCC as shown over here. The output voltage will stuck at this level plus VCC because output voltage can't be greater than this. What I am saying is that if I will repeat, if VD is say 16 microvolt, the output is A, we are assuming 10 raised to the power 6 as the voltage gain multiplied by 16 microvolt. So VO according to this expression is 16 volt. but the output voltage, maximum output voltage cannot exceed plus 15 volt level, which we have assumed over here. So with this, if the differential voltage is greater than 15 microvolt, with this amplification, voltage amplification 10 raised to the power 6, the output voltage will stuck at plus. And if the differential voltage on the negative side, if it exceeds a minus 15 microvolt level, the output voltage will stuck at this. So this mode is known as plus saturation mode, when the output will stuck at plus VCC, and minus saturation mode means when the output voltage will stuck at minus 15 volt or minus VCC. So when the differential voltage is within the range of minus 15 microvolt to plus 15 microvolt, the operational amplifier will be in linear mode. This is very important thing. Now again, what is the output voltage? VO is AVD. As I have shown over here, VO is AVD. VO is AVD. A is voltage amplification. VD is differential voltage, or VD, VP minus VN. It can swing between these two values, plus VCC and minus VCC, or we can show VD can swing between these two. Values. So if we assume, again I will repeat, if plus VCC is 15 volt and minus VCC is minus 15 volt, and we are assuming A 10, then VD over here will be less than I will say 15 microvolt, and over this is minus 15 microvolt. Means when this VD, the differential voltage applied at the inputs of the operational amplifier, is less than 15 microvolt and greater than minus 15 microvolt, the operational amplifier is in linear mode, as I have shown over here. Now the simplified model of an operational amplifier. As you have seen, this is the symbol of operational amplifier with the output voltage, with inputs, VP non-inverting input and VN inverting input. Inside the operational amplifier, we have input resistance, and the output resistance, and a dependent voltage source. Note that in the previous lecture you have seen that in the model of this operational amplifier there are transistors, about 20 transistors, and resistors, several resistors, and I think this is a diode over here. The overall behavior, the input-output behavior of the operational amplifier can be perceived as shown over here, as if we have a dependent voltage source and a resistance RO and this RI, resistance RI. It does not mean that if we take just one resistance and one resistance over here and a dependent voltage source over here, with these three circuit elements we can construct an operational amplifier. No. It is basically a big circuit as I have told you, around 20 transistors and 8 to 10 resistors and a few diodes. It is the voltage and current behavior observed at the inputs and output, due to which we perceive that it can be modeled as the three circuit elements over here: input resistance, output resistance RO, and AVD. Typical values of Ri, it is between 10 raised to the power 6 to 10 raised to the power 12 ohm. Input resistance, very high value, and output resistance, it varies between 10 ohm to 100 ohm. Now, here we see that input resistance is much greater than output resistance, much greater than, and the voltage amplification, we call it open loop voltage amplification, is typical values. The range of typical values is 10 raised to the power 5 to 10 raised to the power 8. Now, we proceed further. To an ideal model. Note that engineers they use an ideal model of a device or a circuit, and then they try to approach to the ideal model. Closer the better. So in ideal model, we will assume that amplification, voltage amplification, this is the open loop voltage amplification approaching infinity, and the resistance Ri, it is approaching infinity, and Ro, it is approaching 0. So with these assumptions, this model over here can be redrawn. Reference ground, this is AVD, and this is VO, and at the input here, at the input side, so this Ri, as this Ri is approaching infinity, we have seen over here Ri approaching infinity, so infinity resistance means it is open. And while this is non-inverting input and this is inverting input, labeled as Vp and Vn. So this is a model of ideal model of an operational amplifier. Due to this ideal model, Vp minus the difference between these two inputs, non-inverting and inverting, the voltage difference over here, will be 0 volt. It means that Vp is equal to Vn. If this Vp is equal to Vn, then the difference Vd will be 0. And due to this resistance Ri, infinite input resistance, the current Ip is 0 and current In is 0. What I am saying over here, look at over here, the resistance over here is infinity. So as infinity, this current will be 0 and this current will be 0. So these are assumptions we will be using in the following discussions, and we will be analyzing operational amplifier circuits using these conditions of A, Ri, and Ro. Using this ideal model, we will now discuss operational amplifier based circuits. So first we will discuss non-inverting operational amplifier. In the non-inverting operational amplifier, we have operational amplifier which is non-inverting. It is this. This is Vp, this is Vn, and if we have a resistance R1 and another resistance R2, and if we use an input signal Vs over here, later we will not use these labels Vp and Vn. It is understood that the voltage at this input with respect to this ground is Vp, and voltage at this input with respect to this ground is Vn. Because we know it, therefore we will not use these labels. Now, how to analyze this circuit? Due to the ideal model, look at this, due to the ideal model, what we have said? We have said that Vp is equal to Vn. Again, I will label Vp is equal to Vn. Means the voltage difference over here, this is 0 volt with this polarity. The voltage difference is 0 volt. And the current entering to this Ip is equal to 0, and current entering to this input In, this is also 0. Now, due to the voltage, this is very interesting thing over here. I am going to tell you that as the voltage difference, this voltage difference, which is Vp minus Vn, this voltage difference is Vp minus Vn, Vp minus Vn. This voltage difference is 0. So, if this voltage difference is 0, then the voltage at this node, the voltage here and the voltage here, because it is just one node, the voltage here will be same. So, here voltage is Vs and here the voltage will also be Vs, because the voltage difference over here is 0. Now, we write node equation at this node, I have highlighted over here, at this node. Writing node equation from the previous lectures, you know what is this current? This current is Vs divided by R1. And now what is this current? This current is due to the direction of this current, this is Vs minus Vo divided by R2. Plus there is another current, this, and this current is I entering to the inverting input. This is equal to 0. So, we have written the node equation. This is node equation. Now, what is our assumption? Our assumption is that this I inverting, this is equal to 0. Now, simplifying this, so this is Vs and 1 over R1 plus 1 over R2, this is Vo over R2, and Vo is equal to R2 1 over R1 plus 1 over R2 and Vo. So, this is equal to R2 over R1 plus 1. So, this is, so you can write it 1 plus R2 over R1, this is Vo. As resistors are positive, R1, R2 are positive, therefore the voltage, output voltage is also positive. Positive means, look at the circuit diagram, this is the polarity of this output is positive with respect to this ground. And we can adjust this VO, sorry, this was VS, this was VS, and this was also VS. Say for example, we want to have 3 times Vs. The output voltage is 3 times Vs. How we can do it? It means 1 plus R2 over R1 is equal to 3, which means that R2 over R1 is equal to 2, and which means that R2 is to R1. So selecting appropriate values of R1 and R2 due to this. Of course, there are some limitations on the values of R1 and values of R2. You can't say that R1 is 1 ohm and R2 is 2 ohm. If R1 is 1 ohm, R2 is 2 times R1. So these resistances can't be so low. Or R1 is 1 mega ohm and R2 is 2 mega ohm. This is also not a practical choice. So there is some limitation on the minimum and maximum values of R1 and R2. You will learn in the following examples as well as in the following courses in electronics. So this amplifier is known as non-inverting amplifier. Non-inverting operational amplifier, non-inverting amplifier based on operational amplifier. I want to draw a line why it is. So then inverting amplifier. In inverting amplifier, based on op-amp, we take operational amplifier and this is VO. Note that we don't show plus VCC and minus VCC. We don't show these because it is understood that we have it. And in here, mind the input, non-inverting input is grounded and we have a resistance, say R1, and we use input over here. And there is a resistance which is also known as feedback resistance, because it connects output to the input side. It's a feedback resistance. So in the previous example, this is also feedback resistance because it connects the output to the input side. Now in here, if we write node equation here, we know that this current is entering into the non-inverting input, and the current, we assume all the currents are flowing away from this node, and let us call it Vx. Write node equation. What is this current? This is Vx minus Vs divided by R1 plus what is this current? This is Vx minus Vo divided by R2. to what is this current, this I entering into the inverting inputs, and then we use our assumption that this I entering into the non-inverting input due to infinite input resistance is 0, and we rearrange this equation. So this will be 1 over R1 plus 1 over R2 Vx minus Vs over R1 equal to Vo over R2. Now what is Vx here? As we have seen that the voltage over here is equal to 0, means Vp minus Vn, this is equal to 0 in the model of an ideal operational amplifier. So it means that the voltage is same, voltage here and voltage here. So these two inputs are at the same voltage level. Initially it looks very strange, but you will be familiar with it. So as the voltage difference Vp is equal to Vn, so this is at ground level, connected to ground. Due to the 0 volt difference over here, we can see that this is also at the ground level because voltage difference is 0. This is connected to actual ground, but due to the properties of the ideal operational amplifier, the voltage at this node is also ground, the ground voltage, but it is not connected to the ground. It is due to our assumptions we have used in the ideal model of an operational amplifier. So this is known as virtually grounded node. It is due to our assumption. So Vx over here, Vx will be 0, and due to that this term will go, and Vo will be equal to minus R2 divided by R1 and Vs. So as R1, both R1 and R2 are positive quantities, therefore it is KVs, where K is R2 divided by R1. So it is this negative sign due to which it is known as inverting amplifier. Say for example, we have R1 equal to 10K and R2 is say 20K, and V output is minus R2 divided by R1 and Vs, this is minus 2 Vs. So it means that if Vs is 1 volt, Vo is minus 2 volt. And later you will see that if the input voltage is sinusoidal over here, if this is Vs, the output voltage minus 2 Vs, output voltage minus 2 Vs, it will be like this, minus 2 Vs. And if Vs is say minus 1 volt, V output will be minus 2 minus 1 because Vs inputs. So this will be equal to 2 volt. So just see the polarity. If the input voltage is negative, output voltage is positive. If the input voltage is positive, output voltage is negative, and that is why it is known as inverting amplifier. Now, next example, voltage follower. In voltage follower, we use an operational amplifier as shown over here. So we apply the input voltage or signal at the non-inverting input, and the inverting input, it is connected to the output over here. This is a very simple circuit, but it may create some confusion. As we have said before, if you see above, in the ideal model, what we have said in the ideal model, operational amplifier, in the ideal model over here, we said that Vp minus Vn is equal to 0, or the voltage at inverting input Vn is equal to the non-inverting, and the currents entering to the inverting and non-inverting is equal to 0. Therefore, as the voltage here and the voltage here, both voltages are same with respect to a ground over here. With respect to a ground, the voltage here and here, these two voltages are same. So what is the voltage difference between these two? This is equal to 0 volt. So if the voltage, if there is no voltage difference between these two, the voltage here will be Vs, and it is very clear that output voltage, this output voltage is equal to Vs. So output voltage is equal to Vs. This is very strange. You can say that if we have a voltage input, and say this is a simple a wire will serve the purpose. In it, V output is equal to V input or V signal, input signal. But we have discussed an example perhaps in the previous part, that output voltage is equal to, the voltage gain is equal to 1 if the output voltage is equal to the input voltage, which is known as the voltage gain, it is equal to 1. However, the current gain Ki, which is I0 divided by Is, this current gain may be much higher, and this current gain, when we connect some load resistance over here, so this current I0, so the current gain will be much higher, and the extra current, but here the current over here, what we have assumed, what is the current entering to the non-inverting input, we have assumed 0 in the ideal model. But the current gain over here, the current at the output is I0, which is flowing through RL, and here we are saying that this is very high. So from where the extra current is coming? Extra current is coming from VCC plus VCC and minus VCC supply. Extra current is coming from these two VCC inputs over here. Then our next circuit is the summing amplifier, or sometimes we call it adders. In summing amplifier, we have operational amplifier, VO, and non-inverting input, inverting input, and we have say V1, we apply voltage here through a resistance R1, we apply voltage here and it is R2, and we connect it to this, and we use a feedback resistance which connects output to the input, and we call it RF, and we connect. This is very important. You will learn the reason of connecting the feedback to the inverting inputs for negative feedback. Now, what we have assumed, this current is I entering into the inverting input. So I entering to the inverting input is 0. Likewise, I entering into the non-inverting is also 0. And we are also saying that Vp minus Vn in the ideal model is 0. Vp is equal to Vn. So this is Vp with respect to this ground, and this is over here, this is Vn with respect to this ground. So as Vp is equal to Vn, we can say that as this Vp is connected to ground, this is also at ground level. This is also at ground level. I am showing it with the dotted lines because it is not actually connected to ground. It is due to our assumptions of ideal model that the voltage here is 0 volt or ground, and the voltage difference between these two is 0. Therefore, this is also at 0 voltage level. Now we write node equation. So writing node equation, so it will be easy if we just use a voltage variable over here, say Vx is the voltage, and we write node equation. So writing node equation, current leaving and current leaving and current leaving through this RF and this current. So 4 currents are leaving the node. Actually, it is not possible that 4 branches, when 4 branches are connected to a node, then all 4 currents are leaving that node. It is not possible. Some current, at least one current, must be going towards the node, flowing towards the node. But these are our reference directions of currents in writing equation at this node. So writing equation at this node, what is this current? This is Vx divided minus V2 divided by R2. What is this current? This is Vx minus V1 divided by R1. What is this current? This is Vx minus Vo divided by Rf. And what is this current? This current is I inverting. Our assumptions, before we apply our assumptions, I will rearrange it. This Vx 1 over R1, this Vx 1 over R2, and this Vx 1 over Rf. So these are the coefficients of Vx term. Then we have V1 term over here. This is minus V1 over R1, and then this is V2. This is minus V2 over R2, and then we have VO. I will write this VO on this side over here. This is VO divided by RF, and then this current. So I will write it as such over here. Now what we have assumed, due to our assumptions, this is 0 and this is 0. Therefore, these two terms will be cancelled, and from here we can say that output voltage is equal to minus Rf over R1 V1 minus Rf over R2 V2. R, it is minus Rf over R1 V1 plus Rf over R2 V2. R, minus K1 V1 plus K2 V2, where K1 is RF over R1 and K2 is RF over R2, and we can select appropriate values of RF and R2 in order to generate an output like this. Say we want minus 2V1 plus say 3V2, so we will select RF over R1 equal to 2, and we will select RF divided by R2 equal to 3. So of course there are some limitations and on the minimum and maximum values of R1, R2 and RF, and you will learn these things in higher level courses. So this is known as inverting amplifier. This is known as summing amplifier, or sometimes inverting summer. Inverting summer means you see it is summing, it is amplifying the input signals. It is amplifying the input signal V1 multiplied by 2, amplification is 2, the amplification of V2 is 3, and this is the addition, and due to this it is the inversion. Say for example V1 is say 2 volt and V2 is say 4 volt, then VO is equal to 2 multiplied by 2 plus 3 multiplied by 4. This is 4 plus this is 12, and this is minus 16 volt. Is it possible? Is it possible? Before that we have said that VO maximum should be less than or VO maximum, sorry, this is equal to plus VCC, and VO minimum is minus VCC. So if this is the case, as I have shown over here, it means that the operational amplifier is operating in its saturation mode, minus saturation mode. So if we want to implement this equation, we should avoid minus saturation mode or plus saturation mode. Then in the following discussion I will present few more examples. These examples will be operational amplifier circuits, examples based on operational amplifier circuits or active circuits.